Hi, I'm Marian Ara and I'm going to discuss the concepts of divergence and curl of vector function. Another important function defined on a vector field is divergence, which is a scalar function. When we say scalar function, it is a real number and it has no direction. Definition of divergence of a vector field. The divergence of function x and y in plane is equals to mi plus mj, while in space it is equals to mi plus nj plus pk. Divergence of a vector field. Dot product notation used for divergence comes from considering delta as a differential operator as follows. Delta times function x, y, and z is equals to partial derivative of x with respect to partial derivative of xi plus partial derivative of yj plus partial derivative of jk times mi plus mj plus pk. Finding the divergence of a vector field. Find the divergence at 2, 1, and negative 1 for the vector field. So for the solution of this, it will be to discuss on another video made by Leo King. So let's proceed to the concepts of curl of vector. Divergence can be viewed as a type of derivative of f in that, for vector fields representing velocities of moving particles, the divergence measures the rate of particle flow per unit volume at a point. In hydrodynamics, the study of fluid motion, a velocity field that is divergence-free is called incompressible. When we say divergence-free, it happens when the function is equals to 0. So it is called in hydrodynamics as incompressible, and in study of electricity and magnetism, it's called solenoidal. Curl of vector field. The definition of the curl of vector field in space is given below. Curl of function x, y, z is equal to mi plus mj plus pk. If curl f is equals to 0, then f is said to be irrotational. Curl of vector field. The cross product notation used for curl comes from viewing the gradient delta f as the result of the differential operator delta acting on the function f. In this context, you can use the following determinant form as an aid in remembering the formula of curl. Curl function x, y, z is equals to delta times function x, y, z. This is just the determinant of I, j, and k, and the partial derivative of x, y, and z, and p. Finding the curl of a vector field is again will be discussed by Leo King. So this is the end of my report. Thank you.
The divergent of the vector field is partial derivative with respect to xi plus partial derivative with respect to yj plus partial derivative of zk. Find the divergent 2, positive 1, negative 1 for the vector field x cubed y squared zi plus x squared zj plus x squared yk. First, we must get the partial derivative of x for the first equation, partial derivative of y with the second equation, and the partial derivative of z with the third equation. And we get the answer of 3x squared y squared z. Then, at the point of 2, positive 1, negative 1, we just substitute the value 2 with x, positive 1 with y, and negative 1 with z. And then 3 times 2 squared times 1 squared times negative 1.
Hi, I am Jen Trinidad. Today, I'm going to discuss about the curl of a vector. First, let us talk about what curl of a vector means. Curl of a vector measures the rotation or the spinning effect. The magnitude represents the strength of the rotation or how fast it would rotate. We can determine the direction of the rotation by the use of the right-hand rule. Curl of a vector is denoted by curl F or delta times F. It is the cross product of the differential operator, also known as partial derivative operator, and the vector field F. We can determine the cross product by evaluating the determinants where the first row will be I, j, and k, and for the second row, it is the differential operator with respects to x, respects to y, respects to z. And for the third row, it is the components of the vector field F. Then, we will come up with this kind of solution. It is the cofactor expansion method. For example, find the curl F of the vector field given by fxyz equals 2xyi plus x squared plus z squared j plus 2yzk. First, we need to put ijk in the first row, and for the second row, it is the differential operators with respect to x, y, and z, and for the third row, it is the components of the vector field F. So, for the first row, we need to put 2xy, and for the second row, x squared plus z squared, and for the third row, it is 2yz. To get this, we need to use the cofactor expansion method. Then, we will get the partial derivative of this. First, we will get the partial derivative of 2yz with respect to y. So the answer is 2z. Then, we will get the partial derivative of x squared plus z squared with respect to z. As you can see, x squared will be considered as 0 because there is no z beside it. So, we are left with z squared, and the derivative of z squared is 2z. Next, we will get the partial derivative of 2yz with respect to x. There's no x, so this will be 0. We will get the partial derivative of 2xy with respect to z. There's no z in here, so it will be 0. Then, we will get the partial derivative of x squared plus z squared with respect to x. Z squared will be considered as 0. So, and we are left with x squared. So, the derivative of x squared is 2x. Then, we will get the partial derivative of 2xy with respect to y. So, the answer is 2x. And after this, we are going to subtract 2z minus 2z equals is 0. 0 minus 0 is 0. Then 2x minus 2x is 0. Therefore, the final answer is 0. Because f curl is 0, therefore we can say that this is irrotational.
Hello, I'm Nathaniel Noveno, and I'm gonna report another example of a curl vector. So in this example, we're gonna determine the curl of the given vector field and determine the curl vector at the given point. So in order to do that, we have to operate on, we have to take the determinants here. So in the first row, we have ijk. Second row is we have the the partial derivative operators, and the third row is we have the components. So here, we're gonna have this kind of form, which is the components of y. In order to get this, as we have to disregard this first column and take the second column and the third column. This is the second column and this is the third column. And the components of j, which is gonna be a negative component, is in order to get this, as we have to disregard the second column, take the first column and take the third column. So here, and then the third component is positive. So here we're gonna disregard the third column and take the first column and second column. So this is the first column and this is the second column. So to get the determinant of this is we have to get the product of negative 2xz and the partial derivative operator with respect to here, minus the product of this one, minus the product of this one. So that's gonna be the later I'll show you the values of these components. And here for the negative component of j is we have to take what do you call this? The product of this one, of this two, the product of this two, minus the product of this two. And then the positive component of k, which is the product of this one, of this two rather, minus the product of this two. So this will be the outcome of that. So after that, this is gonna be the outcome of that. What I'm saying. Here's the product of those two, the I components. Sorry, disregard this sign. And here we're gonna have the partial derivative of yz with respect to y, minus the partial derivative of negative 2xz with respect to z. And for the negative components of z, we're gonna have the partial derivative of yz with respect to x, minus the partial derivative of x squared z with respect to z, and the positive components of k is the partial derivative of negative 2xz with respect to x, minus the partial derivative of x squared z with respect to y. Here, as you can see, there's no x here. There's no x here. So in the outcome of this will be 0. Okay, anyways. So here, same as here. Since there's no y here, there's nothing to be differentiated. So it's gonna be 0, and constant is gonna be 0. So the outcome of this will be 0. Next, we have this is gonna be an outcome of that. So the I component, the j component, and the k component. So here's we're gonna have the z minus the quantity of negative 2x. For j component is negative, so 0 minus x squared. For the k component is negative 2z minus 0. And this is gonna be the outcome of that, the simplest form of the components. So to find the curl vector, the curl vector at the given point, here we are given the points. So we're just gonna substitute the values of the point in their respective variables. So this is x, this is y, this is a. So z, which is 1, plus 2 times x, 2 times 6 is x. This is x squared, so we're going to have 6 squared, minus 2z, to negative 2 times 1, to negative 2 times 1. So this is going to be the outcome. So here we have the curl vector at the given point, which is 13, 36, and negative 2. So that's it. That's
Test for conservative vector field. A conservative vector field is a vector field that is the gradient of some function known in this context as a scalar potential. A conservative vector field is also irrotational. A vector field V is said to be conservative if there exists a scalar field phi such that V is equals to change in phi. To test for the conservative of vector field, the partial derivative of f1 with respect to y should be equal to the partial derivative of f2 with respect to x, and the partial derivative of f1 with respect to z should be equal to the partial derivative of f3 with respect to x, and the partial derivative of f2 with respect to z should be equal to the partial derivative of f3 with respect to y. Example: given this integral, x squared minus z e raised to y dx plus y cubed minus x z e raised to y dy plus z raised to 4 minus x e y dz. The partial derivative of f1 with respect to y should be equal to the partial derivative of f2 with respect to x, which is negative zey. The partial derivative of f1 with respect to z should be equal to the partial derivative of f3 with respect to x, which is negative ey. The partial derivative of f2 with respect to z should be equal with f3 with respect to y, which is negative xey. Therefore, the curl is 0, and the f is conservative.